Am I still audible? Because it seems
Yes.
that my system froze. Okay, somehow my laptop seems to have frozen. And now oh. Unfortunately, the laptop is still picking up my noise. Hold on. Okay. I'm just trying to rejoin using my laptop, which crashed. But now, once I get back, I will talk to you. Okay, I'm back. I was trying to present my screen, and that froze my system somehow. Let's see. So can you see my screen now?
Yes.
Okay. So let me just try. Let's not waste time trying to recover the previous result. For the time being, let me just remind you that the WKB method essentially gave us the Bohr-Sommerfeld quantization condition. Oops. So if you have x along this and v of x along this, and let's say this is your energy E, these 2 points are the 2 endpoints of the or turning points of the motion. And what we have is this condition that if you integrate from A to B, p of x dx, which is of course the same as integrating from A to B, square root of twice m e minus v of x dx. So how much is this going to be? According to Bohr-Sommerfeld quantization condition, this quantity is going to be?
N plus half.
Yes?
Sir, n plus half h cross pi.
N plus half h cross pi, not 2 pi, right? You remember that Bohr-Sommerfeld condition, the way we stated it is if you divide this by 2 pi, you get n plus half h cross. But that is actually for this quantity. a cyclic integral over a complete cycle. And here you are not integrating over a complete cycle. Here you are integrating from A to B only. The complete cycle would involve A to B and back from B to A. And because P changes sign, P is positive when you're going from A to B and negative when you're going from B to A. The B to A integral actually happens to end up being exactly equal to the A to B integral. And so this is really half of the total cyclic integral. So it's n plus half h cross pi. So that is for just the original energy E. Now the point is, if suppose the potential energy is changed somehow, so maybe I'll just use a different color. This is your new potential energy. So instead of the original V, now you have V plus delta V. So we would expect the energy also to change to E plus delta E. And that means the turning points will also change. This will be A plus delta A now, and this will be B plus delta B. So if you use the Bohr-Sommerfeld quantization condition for this changed potential, what you will get is integral from A plus delta A to B plus delta B, because these are the turning points now. Square root of twice m E plus delta E, because that's what the new energy is going to. The new energy, of course, is going to be different. Minus V minus delta V dx. This thing has to be the same as n plus half h plus pi, because that's the quantization condition anyway. Right? And then this is the relation. And we also know, of course, that this is the same as A to B square root of twice m E minus V dx. So, by the way, this is something which actually motivated Bohr in the first place to figure out this kind of a relationship. It needs a bit more advanced classical mechanics than you've studied so far, but this kind of quantity is actually called an adiabatic invariant. And using basic ideas of classical mechanics, Bohr could figure out that this quantity should come out to be some kind of a constant. And that's why he proposed his original quantization condition. It didn't just come out of the blue anyway. So a lot of classical mechanics went into it. But for the timing, we have already derived this using quantum mechanics. So we're just going to take this for granted, at least as an very good approximation, which follows from WKB. This is going to work. Okay. So the next step would be, we wanted to look at how much. So this thing, of course, if delta E is so let's leave the small quantities. Delta E will be, since we are only considering small perturbation, delta V is small. That means delta E, the change in energy, will be small. Delta A, the shift in the lower or the left hand turning point, will be small. So will delta B. All of these are small quantities. So what we are looking at is how much does this side change because of this shift from V plus delta V. And actually we know that the change has to be zero, because if you did not have any delta V, this will of course not be there, this will not be there, and so on. But that is exactly this, right? All we are claiming is that even when you have shifted V to V plus delta V, this quantity will not change. At least as long as WKB is going to work. So what we have here is we need to calculate what is the change here. So let's figure out the changes. There will be a term delta A into whatever first change occurs due to the first order variation of A, then delta B into whatever variation occurs due to that, plus delta E into whatever variation occurs during that, plus delta V into whatever variation occurs during that, due to that, and all of these have to together add up to 0. Now, the question that Rajrupa asked was basically this. In this whole calculation, we said, let's just worry only about delta E into this and delta V into this. Let's simply forget about these two terms. Now, why is that? That is the question. Okay. Now, for this, let me remind you of this important property. Suppose you have any such integral fx a to b fx dx, and you want to find out how much does this integral, of course, what does this integral depend upon? by the way, an integral like this? What does it depend upon? Does it depend on x?
The limit points.
It depends only on the two limits, right? A and B. It does not depend on x. X is a dummy variable. Of course, there could be some parameter inside the integrand. It would depend on that parameter as well, but it definitely depends on A and B. So if you are going to just vary A, say let's say I just vary B and nothing else, then delta I will be what? Delta B into how much? Can anybody tell me that? If I'm going to just change B and nothing else, then the first order variation in the integral will be the change in the limit delta B times what? Elementary calculus. Yeah.
Functional value at B.
Value of the
Functional F.
the integrand at the end point, right? Well, this is straightforward, right? Everybody knows, you should know this result. If you don't, at least the proof is trivial. All you do is, if you change B to B plus delta B, let's say, then you're really doing this integral, right? So what is the difference between the two? It's really nothing but B to B plus delta B fx dx. That's the difference between this one and this one. And if the interval B to delta B is small enough, now I'm deviating from pure or proper mathematics, but I'm just giving an argument which can be formalized if you want. But the basic idea is if the interval delta B is small enough, then this integral, of course, is delta B times the value of the function at B, right? Because all we are saying is once the interval is small enough, then the function doesn't get much of a chance to vary. So you can replace it by its initial value. And this delta B into FB, that's the variation. Of course, when you talk about the lower end, it's going to be delta A into FA with a minus sign. Minus sign because simply because if you increase the lower limit, that actually decreases the interval over which the integral is occurring. And in addition to that, if f actually, if f were varied, then you would also have integral from A to B delta f dx. So three contributions: one because the limits are varied, two of them because of the upper limit and the lower limit, one from the variation of the function itself. Here, what I'm claiming is, in our case, I get a variation from the variation of the function. So delta E and delta V, when they change, of course, the integrand changes, and that's what we are talking about here. In addition, you have a variation. You should have a variation due to the lower limit and the upper limit, and I'm claiming that those two variations can be ignored. Now, the question is, what is the value of this quantity, of this integrand at the lower limit? At A, when you put in x equal to A, how much is this integral? How much is this integrand? Yes? A is not any arbitrary point, right? A has a very specific meaning. The point A and the point B have very specific meanings, right?
Root over of 2m into delta E minus delta V.
It's twice m into delta E minus delta V squared root of, not exactly that, but anyway. Yeah, the point is, Aniruddha said 0. 0 is not exactly right in the sense that when you, it's exactly 0 at A plus delta A, right? This integrand is exactly 0 at A plus delta A because A plus delta is found out by to be that position by demanding that it's the point where the potential energy V plus delta V exactly matches the energy E plus delta E, right? And so on similarly for B plus delta B. So this would actually exactly vanish at A plus delta A. But as at A, it will not exactly vanish, but it will deviate from 0 by an amount which is proportional to delta E and delta V, right? Is it okay? I don't even care how So the point is this function vanishes at delta E equal to delta V equal to 0. So when you go away, when you take a value of delta E which is not 0, the first variation will be proportional to delta E. So whatever you have multiplying delta A here will be delta E minus delta V into something. Did that make sense? Simply because without these two terms, this quantity would have been 0 exactly at x equal to A. With these terms, it's not exactly 0 at x equal to A, but it deviates from 0 in the first order. Is that okay? But if you accept that, you should now be able to see why I am ignoring it. I'm ignoring it because delta A is sitting outside, right? To multiply that by delta E minus delta V, what you get is a second order variation, not a first order variation. So, as far as the first order variation is concerned, this term is 0. So is this, for the same reason. Because the upper limit and the lower limit are the turning points where the integrand would vanished originally, how much, when you move over to the new value, the integrand will change a bit, but it will change in proportion to the rate at which your arguments change, right? And so if delta E and delta V are first order, you're going to get a first order variation in the integrand. In the actual integral, the variation will be delta A times this change in the integrand, which is of course nearly 0. And in fact, it's definitely 0 to first order. Is it okay with everybody now? Yes? If I don't get a response, I'm not very sure whether I was even heard.
Yes, sir.
Did it make sense?
Yes.
So Aniruddha gave a reasonably correct answer at the very beginning when he said that these two endpoints, at the two endpoints, the integrand is 0. It's not exactly 0, but its deviation from 0 is only at the first order. And since it's multiplied by a first order quantity, can ignore that change at the first order, which is what we are doing. So the first order deviation will only come from delta E and delta V terms, which is what we use to derive this WKB prediction for delta E, which as we found out was close to the first order Rayleigh-Schrodinger prediction, but not exactly the same. It matches the Rayleigh-Schrodinger expression very closely for large values of n, but not for small values of n. But even for small values of n, it's not too bad. Okay, any other questions? Okay, if not, I will start talking about, I talked about the adiabatic approximation the last day. The proof, of course, was rather complicated, and I'm not sure most of you stuck through till the end of the proof, but the proof, the theorem actually is pretty simple. It essentially says this, that if you start at an instantaneous eigenstate of a Hamiltonian, and you kept on varying the Hamiltonian slowly, then of course the Hamiltonian will change with time. As a result, its eigenstates will also change with time. And although the Schrodinger equation does not tell you that the time variation of the initial state will follow the instantaneous eigenstates of the Hamiltonian exactly, it does say that if you vary the Hamiltonian slowly enough, if you start with an instantaneous eigenstate of the Hamiltonian, the system stays in an instantaneous eigenstate of the Hamiltonian with a very high probability. So, and let me just point out that the one example that we worked out, exactly solvable problem that we worked out, the one with this one, this immediately violated that. Okay. So let me just remind you what happened here. Here, of course, you could exactly solve the problem, and and this problem is, of course, exactly solvable. You can immediately write this as, say, H psi. Psi, of course, here would be a two-component matrix. And if you solve this H psi equal to IH cross del psi del T, you immediately end up with two equations. IH cross del A del T is alpha T by 2 A, and IH cross del B del T minus alpha T by 2 B. And this gave us an immediate solution for A and B. So A T essentially became AT0. Actually, not T square by 4. This is actually T minus T0 whole square by 4. And BT to the plus I by H cross alpha T minus T0 whole square by 4. So in particular, if AT0 where 1 and BT0 equal to 0, that is, you started at the state 1, 0, then as time goes by, all that happens is the system acquires this phase factor but stays at this level. So once 1, 0, whatever 1, 0, this is what the system actually behaves, this particular system behaves like. Okay, it doesn't change its state at all. Now, while this looks like it actually matched at the adiabatic theorem's statement, it actually does not, simply because if you look at the instantaneous energy eigenvalues, the eigenvalues are easy to see. The eigenvalues are simply whatever you can read off here, right? Just from these two terms. So the state 1, 0 had an energy alpha T by 2 to begin with, and for large negative, sorry, this is wrong. This is for large negative times, alpha T by 2 will be large negative. So state 1, 0 keeps on staying the state 1, 0 and goes, as time goes by, at large negative times, 1, 0 corresponds to the energy eigenvalue alpha T by 2. At very large times also, in fact, at all times, 1, 0 corresponds to the energy eigenvalue alpha T by 2, and 0, 1 corresponds to the energy eigenvalue minus alpha T by 2. However, what is important is to realize that when we say if you are in the state phi 1, you stay in the state phi 1. Phi 1 stands for the, in this case, you have two energy levels. So phi 1 will stand for the lower energy level and phi 2 will stand for the higher energy level. So here what happens is state 1, 0 stays the lower energy level up to this point of time, and then the lower energy level is this one, which is 0, 1. So suddenly at T equal to 0, the lower energy level jumps from 1, 0 to 0, 1. So this is what happens in this particular situation. The adiabatic theorem is violated, and not only is it violated, it's violated completely. Now, that's also not difficult to understand. It's not difficult to understand why, because the basic condition for the adiabatic theorem to work basically is del H del T, the rate at which the Hamiltonian is changing, divided by the energy gap between the eigenvalues or between the eigenstates, or rather, to be more precise, not the energy gap, but the instantaneous energy gap between the eigenstates. That must be a very small quantity. But when you are getting close to t equal to 0, the two energy eigenvalues are very close to each other, or two instantaneous Hamiltonian eigenvalues are very close to each other. That means that no matter how slowly you change the thing, no matter how small del H del T is, del H del T will become very much bigger compared to delta E, the eigenvalue difference, once you're very close to t equal to 0, and the basic condition for the adiabatic theorem will simply fail. Okay. So now there is a very nice problem. In fact, it's not only is it nice, it's a very important problem in nuclear physics and many other, and atomic physics and many other branches of physics, which actually is very similar to the one we discussed, and which is exactly solvable, and which shows perfectly well how adiabatic theorem actually works, and also gives you the reason why this particular version fails. So that's almost the same problem as our problem, except that now you have an alpha t by 2 sitting here minus alpha t by 2 sitting here as before, but the off-diagonal elements are no longer 0. There's an off-diagonal element, and because the Hamiltonian has to be Hermitian at all times, whatever f is sitting here, f star is sitting here. Now, this particular Hamiltonian has instantaneous energy eigenvalues which are very easy to figure out. What are they? Can anybody tell me what the eigenvalues are? Or basically, two energy eigenvalues that this system has which of course in the limit f goes to 0 gives us back our old result that the two eigenvalues are plus minus alpha t by 2. Now the f has changed things somewhat, and now you can clearly see that as time goes by, if you look at these expressions, alpha t by 2 square root of alpha t by 2 whole square plus f mod square, and this one minus alpha t by 2 mod square plus f mod square, you get these curves as so the time variation of the eigenvalues is not like this any longer. It's actually like this. That's one, and this is the other. And now you see that there is no crossing between the energy eigenvalues, right? Unlike this problem where 1, 0 crossed over there, this is what the thing looks like. But can anybody tell me what will the energy eigenvectors be at, will they be dependent on time now? Earlier they weren't, right? 1, 0 or 0, 1. Will the energy eigenvectors depend on time now? Simple question, yes or no? Come on, this is your Hamiltonian operator. This is a matrix, right? Will its eigenvectors depend on time, yes or no? Should be an easy enough question to answer. I'm not asking for what the time dependence will be, if there is any. I'm just asking, will it depend on time? It will depend on time if f is non-trivial. Non-trivial meaning f is not 0. That's what you mean, right? And you will be right. As long as f is not 0, the eigenvectors will depend on time. Now, it's one thing is pretty easy to understand. At very large positive times and very large negative times, at those two limits, you can of course ignore the size of f compared to alpha t by 2, right? For both, when t is very, very large, either very large positive or very large negative, f will hardly be important. So it's easy to see whatever your time dependent eigenguesses are, when t is very large negative, then the eigenket will be 1, 0 effectively. The lower energy eigenket. And when it's very large positive, then the lower energy eigenket will again be 0, 1. Just the same as if f were not there. If f were 0, then 1, 0 would be the lower energy eigenket until you hit t equal to 0. After that, 0, 1 would have been the lower energy eigenket. So this is what the lower energy eigenket's trajectory would look like. That's the eigenvalue trajectory, and it's 1, 0 throughout, and then 0, 1. With non-zero f, the eigenvalue changes according to this particular hyperbolic curve, and along the asymptote of the hyperbola, when you are very far away to the negative keys, the eigenvector will be 1, 0. For very large positive t, this same eigenvector will be 0, 1. And similarly, for the upper energy eigenvalue, E plus or E1, so you have E1 and E2. E2 is the lower one in our notation. So for E1, at very large negative times, 0, 1 will be the energy eigenket. At very large positive times, 1, 0 will be the energy eigenket, simply because when t has a very huge magnitude, f will hardly change anything. But at moderate times, in between, what will happen is that f is going to take over, and as a result, as t varies, the instantaneous energy eigenkets smoothly go over like this. So it depends on time. The time dependence is very easy to figure out. All you have to do is just solve this eigenvalue equation. Now you have already solved the eigenvalue equation. Just plug in the eigenvalue back, find the eigenvector, you will find the time dependence. Okay. Now the question that we are asking is not about the instantaneous energy eigenvectors. The question is, if I start at large negative times, let's say at -infinity, in the state 1, 0, what is the probability that I stay in the state 1, 0 at large positive times? According to the adiabatic theorem, this should be how much? So let me just write down the question for you, that if psi at -infinity is 1, 0, what is the probability that is also 1, 0? That's the question. And according to the adiabatic theorem, this should be how much? Yeah, according to the adiabatic theorem, if the adiabatic theorem is exact, it should be 0. Okay. And we have already seen that according to, then when f is not there, then the answer to this question is exactly 1. If you start at 1, 0, you stay at 1, 0 forever, which means this particular model violates the adiabatic theorem completely when f is 0. But what happens when there is an f? That is the real question. So what we need to do is to figure out how the system evolves in time for obeying the Schrodinger equation as time. And then if you give it the initial condition 1, 0 at large negative times, how probable it will be to give you 1, 0 also at large positive times. So once again, the basic thing that we are trying to do really is this: IH cross del T of AB is So this is the equation we are trying to solve. Or rather, this really is simply two equations. Right? So coupled differential equations. Coupled simply because A's equation has B in it, B's equation has A in it. So I will not solve the equation for you today. I will just leave this as an exercise for you to worry about. You should be able to decouple okay? And once you manage to decouple these equations, okay, let me just give you a hint. What you really should try to do is find an integrating factor and use that first. And that will simplify the left-hand side for both these expressions. And then reintroduce new variables. Basically, A times the integrating factor becomes, so basically A times this is your new A tilde. Similarly, do a similar thing with B. Rewrite the equation in terms of those, and then try to eliminate, then get two easier equations in terms of A tilde and B tilde, and try to eliminate one of the variables in favor of the other to get a second order ODE, which this equation obeys. So that's your homework. So this is set up for the next assignment sheet, because I'm not going to work out the problem for you today, but we will discuss this the next day once I see what your response is like. Okay. Set up the second order ODE, then try to solve this question that if initially A at minus infinity is 1 and B at minus infinity is 0, how much is A at plus infinity and B at plus infinity? I will just give you the answer right now, or at least I will indicate the way the answer goes. The answer essentially looks like this. If you ask yourself how much is A at plus infinity, the answer is this thing, which should be 0 according to the adiabatic theorem, is actually e to the power minus, I've forgotten the exact factors, but most probably is pi by h cross f mod square by alpha. So it's something like this. So this is A at plus infinity. Finding out this answer, this is one of the very few problems in quantum mechanics where you have a non-trivially time-dependent Hamiltonian, and you can still exactly solve the Schrodinger equation for that. Okay, it's an important enough problem because this issue of two levels coming very close to each other and then moving away is something which is observed in many different places, nuclear physics, atomic physics, and so on. And this particular model is a very good model which has been used for various things, including, say, chemical reactions, nuclear transitions, and so on. It's called the Landau-Zener model. By the way, this Zener happens to be the same Zener after whom the Zener diode is named. Essentially, the Zener effect is also related in a way to this model. The Zener effect that you have in the Zener diode, that's also related to the behavior of this model. When we talked about the Zener diode last semester, we just say there's a quantum mechanical result. The quantum mechanics essentially involves an effect like this. Anyway, if you look at the result, see what this is telling you. If f is 0, of course, we go back our old result, that is A plus infinity is 1, right? It just tells us that the system will stay at 1, 0 forever. On the other hand, if f is non-zero, notice that this is a decreasing exponential term, and here it shows that if alpha is very small, then you have a large negative exponent. So this is a very, very small quantity. So for non-zero f, for zero f, no matter whether alpha is big or small, doesn't matter. But for non-zero f, a small value of alpha leads to a tiny a plus infinity. So this means, now notice that adiabatic theorem really says that if you change your Hamiltonian slowly enough, note that here your Hamiltonian time dependence was in the alpha t by 2. A small alpha means the Hamiltonian changes slowly. So if you change your Hamiltonian slowly enough, the probability that the system will go out of the lowest instantaneous energy eigenstate and go into the other energy eigenstate actually turns out to be vanishingly small. At least it drops exponentially with 1 by alpha. So the smaller you make alpha, the better is adiabatic theorem going to work. And that's exactly to be expected. It just says that if you change your Hamiltonian slowly enough, the system stays in the instantaneous energy eigenstate. That's exactly what this result is telling you. So for f equal to 0, no matter how small you make your alpha, this result is always going to be 1. And that's simply because for f equal to 0, the two levels actually cross. And as a result, this basic condition for the adiabatic theorem, del H del T by Em minus En is very, very much smaller than 1. That can never work. That is, that always fails when T is close to 0. So your homework would be to at least write down the second order ODEs and try to solve them. We will discuss other ways, especially ways involving contour integrals, which actually can help you to get the answer without really working out the entire ODE. But that we are going to discuss the next day. I just wanted to give you a flavor of the setting behind the problem. Yeah. Any questions about this? There seems to be no questions about this. So we will now move on to our next topic, which is connected to the adiabatic theorem. Not really a new topic entirely. At least when the topic originally came into the picture in physics, it came in via the adiabatic theorem. Nowadays, that topic has been sort of worked on by many physicists, and now people know how to get these results even without the adiabatic theorem, or at least how to figure out things like these even when Hamiltonian changes rapidly and not so slowly, and so on. But the original formulation is actually still the best one, and I'm pretty sure many of you may have already heard of this, at least because the person after whom this effect is named visited either Kolkata a while ago, of course when visits were still possible, and some of you may actually have been in his lecture. Okay, is there anybody here who actually sat through M.V. Barys' lecture, which occurred when you were in the first year, I guess? Anybody? No. Okay, anyway, if you haven't heard him lecture, well, you missed something, because this was real. So Barys gave a colloquium in either Kolkata about what else Barys faced. But being the modest person that he is, he had a slide near the beginning of his talk where he gave the full name for this effect, and that name had a page full of people's names in it. And Barys was just one somewhere in the corner in this whole thing. Because as Barys is very fond of saying, he just sort of illustrated that this phase is important. many other people had discovered this before him. And it is one of its counterparts. So happens that the Barys phase is a quantum mechanical effect, but it has many counterparts in other branches of physics as well. One very famous counterpart occurs in optics. And okay, I keep on getting confused. You people haven't, did you have an optics lab this semester? The advanced optics lab? Of course, I know it's cruel to ask whether you had a lab at all or not. But was the advanced optics lab scheduled this? Okay, it used to be scheduled in the third year, second sem. Now once we changed our syllabus, it's now gone to the fourth year. So hopefully, if all goes well, you may be able to even work in that lab hands-on, at least next year. So there there's an experiment on something called the Pancharatnam phase. This is a result which involves polarization optics, but which actually captures exactly the same mathematical features that Barys phase does. And in fact, Bary actually calls his phase the Pancharatnam, and okay, not only the Pancharatnam phase, but many other people's names followed by his own name. Then the word phase. Okay, so let's try to understand what Barys phase is. This happens to be a rather recent addition to physics courses, simply because this is a rather recent topic. And how important this is really in physical applications has only been revealed over the last decade or so. So it's a relatively new topic, and new things are still being discovered in it, and new applications are being discovered as we speak. So this is really cutting edge physics, but the basic idea is very simple. The basic idea is something like this. Adiabatic theorem, the theorem that we started with, simply says something like this. If a state at time t0 is in the nth instantaneous Hamiltonian eigenstate at time t0, then at least as long as your Hamiltonian varies slowly enough, as time goes by, psi t will stay phi n rt, right? Okay. Now you know that this cannot be exactly correct. There has to be some. There are other terms, that is, psi t will have probabilities of transiting to other states, not just phi n rt, but as we proved the other day, you can make the probabilities of transitions to these other states very, very tiny, simply by making the variation in the Hamiltonian slow enough. Okay. So we are going to ignore all these other terms for the time being. So all these other chances of violation of the adiabatic theorem, we are simply not going to take into account. However, psi t will of course not be exactly equal to phi n rt, right? Even within the adiabatic approximation. Suppose the Hamiltonian were exactly time independent, let's say. Then if psi t0, so for time independent case, of course, the adiabatic theorem is exactly obeyed, right? Because there is no Hamiltonian variation. If once the energy eigenstate, it stays an energy eigenstate. If psi t0 is phi n t0, here of course the label t0 doesn't really make much sense, because the Hamiltonian being time independent, the eigenstates are also time independent. But then is psi t equal to phi nt? Phi nt is of course the same as phi nt0, but is this correct? If psi t0 is phi nt0, is psi t phi nt? Yes? I'm asking a simple question from time independent Hamiltonian.
Yeah, with an additional phase of.
Yeah. Okay. There may be a phase difference, as Aniruddha says. You said there may be an additional phase. It's not a question of maybe, or not just with the phase is all that happens here, right? If there's
e to the power I ent by h, correct?
So you get e to the power minus. Oops, sorry. You just get e to the minus IEN t minus T0 by H cross phi n t. Here the t label for phi n t is redundant because phi n T0 and phi n t are one and the same. You just pick up a phase. Okay. And this phase is exactly where the dynamics of the system is. That's all that happens. Right? Of course, because the state only changes with a phase, you say that nothing physical is changing and the system is in a stationary state. And you all know all that. But the state actually changes and picks up a phase. Fine. So what do you expect happens here? So even when there is a time-dependent Hamiltonian, provided the time dependence is slow enough so that your adiabatic theorem works, once phi n are T0, forever phi n are T. Okay, of course, phi n are T0 and phi n are T are different states in general, but at least what we can say for sure is that once you start with this state, you stay in the corresponding instantaneous Hamiltonian eigenstate, but you will pick up a phase, right? So you will get some phase which will depend on time. Now, that phase, our first guess could be that it's a phase very much like this, except that it cannot be like this because En is not a constant any longer. But then the next obvious thing that could be is En, of course, changes because the Hamiltonian changes through the R. This is very important. Hamiltonian changes because the R, the parameters, R1, R2, R3, which describes the Hamiltonian, they change with time. So En is actually a function of R, but R changes with time. So so you get an En RT dependence. Now, you can't say it's En RT into T minus T0 by H cross. This will, of course, make no sense, right? Why not? Because why should only the value of the Hamiltonian at the final time, why should that thing be the one which contributes? After all, that has been the value of the Hamiltonian only at the end. The Hamiltonian took all values in between, right? So what you would expect is something like this. Just like in the WKB case, we didn't say P into X by H cross, we said integral of Px prime dx prime by H cross. Basically the same thing. The energy eigenvalue changes with time, and this is an extra phase factor that you would expect. And when you do get this is called the dynamical phase. And this is exactly what would be the only contribution to the phase if the Hamiltonian were time independent, right? But the actual Hamiltonian is not time independent here. It's a slow varying Hamiltonian, but it has a time dependence. And as a result of this, this may not work out exactly. In fact, it does not work out exactly. After all, the time evolution has to obey the Schrodinger equation. So what we will see is that the Schrodinger equation says that in addition to this phase, which we expect anyway, which is a sort of generalization of this one, you would get a new phase term which depends on time. Okay. Yeah. So basically, all we are saying is we are breaking up the overall phase term, which this phi n r T0 will pick up as it evolves in time, as the system evolves in time, into two pieces. One piece is what you would expect from the dynamical terms anyway. Another piece, the additional piece, this is what is called Barys phase, or simply the Barys phase. The Barys phase, of course, is gamma nt. This is the Barys phase. Okay. Now, you might ask, what's the big deal? Why do we need to break it up this way? One answer is what I gave you, that you can think of this being the phase we expected anyway. This is the whole phase that we have. So whatever extra we get, we are taking a look at that. But there's a much more important reason why we separate this part and this part out, and that's what we are going to discuss now. Okay, so let me just go over and so basically, this is the equation that you expect the system to obey. And what we are saying is my wave function psi t obeys the adiabatic theorem closely. So up to very small terms, this is phi n RT0 times a phase factor, which is it's a minus T0 to T En RT prime T prime by H cross minus I gamma n of T. Now, what will decide what gamma nt is going to be? So if I ask you, after you are proposing that this is the wave function, the state evolves, and I want to figure out gamma nt, what is the tool that we have in our hands to figure out gamma nt? Yes? This is a time evolution of a state, right? Because the only tool we have is a Schrodinger equation, nothing else. To find out gamma nt, what we will have to do is take this expression, plug it into the Schrodinger equation. That's all we can do. And if you do that, you'll get something like this. You'll get IH cross. Then comes the derivative of this thing. Of course, the derivative of this thing will be minus I. Right? That's what comes from this derivative into the whole thing, but that's there anyway. Minus, when I differentiate this with respect to time, what do I get? I get simply minus I by H cross right? Times, of course, this entire phase factor, it is a minus gamma nt, blah, 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 times phi n r. And this has to be equal to the Hamiltonian HRT acting on psi t. So what is this going to be? HRT when it acts on psi t, what will it give you? As far as the Hamiltonian is concerned, this phase factor, this whole factor here, it's just a constant. So the Hamiltonian will go and hit this. And that immediately gives you En RT. Is that okay with everybody? Remember, the phi n RT is an instantaneous Hamiltonian eigenketch. So when the Hamiltonian acts on phi n, you just get En times phi n. And now, how will the gamma t be a well-defined function? Since wave function at any time. Okay, Rahul had a very good question, I guess. At any time t can have any phase of magnitude 1. That actually is an excellent question, Rahul. We will come back to this. Rahul is asking, since we can change the wave phase anyway, after all, phase is not really observable. So how can this gamma at all be a very, okay. Your question is not really posed perfectly because after all, when you decide that this is your wave function, you have to decide once and for all what the phase is. But if you change the phase, and you can change phase different at different times, then physics should not change. So frankly, the answer to your question would be, it seems like this gamma nt is something which you may very well define, but would at least not be physically observable. But we will see that that's really not true. And let's just hold on a while and then you will see why. For the time being, all we are saying is there's some phase which comes out by solving the Schrodinger equation. The Schrodinger equation will give you some value for this. So notice that this phase is same on both sides, so it just cancels. And but there is one more term which I missed out. Can anybody tell me what term? Anubhav was asking, what if we take a superposition? We'll come to that. But for the time being, Rahul's question was, we can't define this phase simply because this phase can be absorbed in the definition. We'll see why not. But before that, let's get the maths right. We have not yet done the maths properly yet. We have missed out one term. Can anybody tell me which one that is? I take this expression, plug it into the Schrodinger equation, and it seems that
There should be a T0 term like REN RT0 term, right? When we
no, there's
differentiate.
no RT0 term. There is no RT0 term. All I'm saying is, why should there be an RT0 term?
Like when we differentiate that definite integral.
Sorry, I think I misled you by my writing. I wanted to sort of overwrite something. This is phi n RT, not phi n RT0.
Okay.
Yeah, but then you're right. I think you are pointing to this term, right? This is of course time dependent, right? This term here depends on time, so you should differentiate that as well. If it had been RT0, then you can't differentiate because T0, of course, is some constant initial time. That wouldn't have had a time dependence, but this one does have a time dependence. This is what you get into the whole phase factor, which cancels again. So you had three terms. Actually, there are three time-dependent pieces to Shaiti. One is this one, our Barys phase, what we are trying to figure out. This one, our dynamical phase, and as well as this phi n RT, the energy eigenkette, which also depends on time. So three pieces which depend on time. When you differentiate that, you get three distinct, separate additive terms. On the right-hand side, of course, is just this whole thing being acted upon by H. So you get one term, which is En times phi n. Now, you should notice that this term exactly cancels out this term, right? So what you end up with is a very simple looking equation, minus I gamma n dot okay, let's cancel out the IH crosses on both sides. So no IH cross here. Minus right? So maybe have I got the signs correct? Let's check. Yeah, he's right. Is that okay? Just cancel out every term. You get minus I gamma n dot. This term acting on phi n times phi n RT is nothing but minus del T of phi n RT. Okay, and this immediately gives me a formula for gamma n dot. The rate at which the Barys phase changes with time. Simply take the overlap of this quantity with the bra phi n RT, and you simply end up with, and move the I to the other side. So this is the formula that we have for the dynamics of the Barys phase. That is, it's going to evolve. Basically, you can find out its evolution by differentiating phi n RT with respect to time, taking the overlap with phi n RT, and plugging in a minus I in the front. Okay. Now this minus I might seem to be a bit of a problem because this seems to suggest, suppose I started with gamma n equals 0. Okay, this is gamma n dot, right? The date at which it changes. What does this expression seem to tell you? What is gamma n? Real or imaginary? So Rahul is saying real, but why are you saying real? Can't you see the minus I stuck in there in the gamma n dot? Okay. Rahul is pointing out correctly, and this is something we discussed in the last class, basically, that this part is purely imaginary. Why? Simply because start with this phi n. I'm not writing the RT because that's just cluttering up the notation. So phi n overlap is 1, right? So if you differentiate that with respect to t, what you get is del t of the bra phi n overlap with the ket phi n plus phi n bra overlap with del t ket phi n. This thing is 0, right? But these two things are actually complex conjugates of each other, because if you look at this, it's really nothing but the adjoint of this. So what we have is this quantity plus its complex conjugate is 0. So this thing sitting here is actually purely imaginary. So because this is purely imaginary, with the minus I in front, this becomes purely real. So if you start with gamma n of 0, it has a real rate of change, so you're going to get a real part. So ultimately, gamma n is just purely real, which is good because because gamma n has to be purely real from the theory, right? Because if gamma n were complex, then this would have a real part, and that would mean the normalization would change with time, and the system will decay or somehow grow. Neither of which are physically possible in this situation. You start with a normalized state, you stay in the normalized state forever, and that's actually managed by gamma n. So gamma n is real, so that's fine. So now comes the question: what is gamma n as a function? As you move along the curve, how much is gamma n? You know gamma n dot. So gamma n is at time t. Let's use gamma n at time t0. We define gamma n at time t0 to be how much? That's pretty easy, because at time t0, you look at this expression. At time t0, psi was psi t0, which was phi n r t0. Exactly this. This integral, of course, vanished. So this factor was 1. This factor would also have to be 1, because all you're saying is phi n r t0 has to be the same as phi n r t0. So gamma n at time t0 was simply 0. So gamma n at time t is simply going to be the integral minus I from t0 to t. So since t is the final limit here, the integrand has to be replaced by dummy variable. In the integrand, it has to be replaced by this dummy variable t prime. Dt prime. This integral is what will give you gamma n. But now let me just remind you of one thing. Why does the eigenvalue depend on time ultimately? Where does the time dependence come from? Remember, we started with H, which was time dependent, but it was time dependent essentially because it was a function of loss of parameters R1, R2, R, let's say capital N. Let's distinguish between this N and this capital N. Capital N number of parameters, 1, 2, and these parameters depended on time. So H's time dependence essentially came from the parameters time dependence. Same here, phi n RT is time dependent because R1, R2, R3 are time dependent, nothing else. So you can easily see that ddt is nothing really but right elementary calculus. If a function depends on several parameters and each of them depends on time, the rate at which the function changes with time is basically each individual function's rate of change times the corresponding derivatives. And this thing can be shorthand. I write a shorthand for this. Grad R so this should remind you of first year basic mathematical physics or maths, whatever wherever you say this. This is a gradient dot displacement vector thing, dot the directional derivative. The only difference here is that there the gradient was in real space, so the vector R had three components x, y, z, and so on. Here the gradient is in some abstract n-dimensional parameter space. But you should actually appreciate that is why we call that parameter vector capital R. Basically, it's like the position vector in parameter space. Okay. So, and just by borrowing that notation, what we can write is ddt of phi n rt is simply this, and hence our gamma n formula. The gamma n is the Barys phase acquired by the nth eigenlevel as time goes by, and that turns out to be simply minus I integral from t0 to t now. Can anybody point out exactly why this form is actually rather nice? What does this really tell you about the time dependence? This t prime dependence. There's the I. Okay. Now, this is the really critical part about this. Why this is different from dynamical phase and so on. And this quantity is also called a geometric phase. So what's geometric about this? If you look at this expression, the integral is being carried out. So all we have done is we have changed our variables from t to r, basically, to this path. Now, what has really happened here? This particular integral, as you wrote it, in the original version, it depended on t prime drastically, right? It had several places where it depended on t prime. In fact, you had to find out phi n at t prime, then differentiate it with respect to t prime, then take the overlap with respect to phi n at t prime, then integrate that with respect to t prime. But when I write it in this form, does it depend on t prime any longer? Yes or no? Of course, you might argue that the integral never depended on t prime in the first place, right? T prime was a dummy variable of integration, right? So it never really depended on t prime. But this at least makes it look like whether you are traversing your parameter points slowly or rapidly, that would make a difference to this integral, right? If you went through the same set of, what this version tells you is that suppose you are in some abstract, let's say three-dimensional, simply because I can draw three-dimensional space. So R1, R2, R3 are just values of parameters. There's no position involved here. And let's say as time goes by, you have some value of R1, R2, R3, and as time goes by, these changes according to this curve. Okay. So as time goes by, this is how the system is, the parameters are changing, and as a result, the Hamiltonian, etc. are changing. Now, what this formula tells you is that whatever phase you acquire here will be completely independent of whether you traverse these points fast. So you suppose you went through the same set of points very rapidly to begin with and then slowed down and went slowly at the end, or you went very, very slowly throughout, or you went rapidly at the beginning then slowed down. As long as you visited the same points in parameter space as time evolves, the precise dynamics of the problem, the way in which the parameters were actually changed with time, that is no longer there in this formula. Gamma at this Barys phase does not depend at all on whether the system was driven uniformly, non-uniformly, slowly at first, even more slowly at later. Doesn't matter at all. You are going to get the same value, which depends only on the particular path which is traversed in the parameter space. Does this point make sense? Yes, no? Well, I can give you a very simple example of something that you have seen before, which works like this. Okay, what example can I think about? The simplest example I can think about is this. There's a work, right? Now, when you write this as in one dimension, this is f dx integral. If you look at the right hand side, this gets even better because since you're in one dimension, v dv is an exact differential, so this integral depends only on the initial and final velocities. But even if you didn't have that result, you would still see that this result will depend only on how the velocity is behaved during the motion, not on how the velocity is changed with x. This is a bit too trivial example, of course, because here you ultimately end up with an integral which depends only on the initial and the final value of the velocity. Here it depends, here this integral will depend on how the r changed throughout, but not on how fast or how slow the r changed. Although there's a catch there. I did say that it doesn't matter whether the r's were traversed very rapidly or very slowly. Of course, if it were traversed very rapidly, that is the things change very rapidly with time, then the adiabatic approximation itself would have broken down. So this fact that this gamma n is not dynamical, it does not depend on the dynamics at all. While that is true, you have to realize that this is actually the phase acquired provided you are proceeding slowly enough. But the details of how slowly you proceed, or whether you proceed uniformly or whether you speed up, slow down, doesn't matter. As long as your maximum rate of change of the Hamiltonian stays well within control so that the adiabatic theorem can be used, this works fine. So any questions about this? Or, okay, let's introduce a new notation here. where an this an is a vector field in our R dimension, in capital N dimensional space. So it depends only on R1, R2, R3, Rn. At different R1, R2, R3, Rn, it has different values. And you can work it out using this formula. Now, does this formula look familiar to anybody? A formula like this? Or at least this quantity, does it look familiar to anybody? From some other branch of physics. Have you seen this ever? Action doesn't really look like this. Something even more which should be even more familiar. Okay, think of it. Think of this in 3 dimensions. If you saw a relationship which looks like this, and let's say looks like this for a closed loop, what would you write this as? Why closed loop? We are going to come to that. So far, we have not talked about closed loops. Yeah, any dot product will look like the work done, but suppose for a closed loop, for example, AR dot DR, I think this, in fact, what I'm relying on is the fact that there is a very standard thing in physics which is written A. And I think you should all know that. Anyway, if you just forget about what this means physically, but if you look at this closed integral, this is, of course, right? Now, does this ring a bell? Curl of A dot ds? In particular, curl of A is what? I'm talking about it's like when I say C, I could mean some other constant, but when I say C in physics, I almost invariably mean one thing, right? If I say curl of A in physics, what do I mean usually? Magnetic field, of course. So we have an analog, and in fact, this is actually the flux through the surface sigma of the magnetic field, right? Now, I just want to point out that there are analogous things that you've already learned about, and in fact, that is precisely why this thing is called capital AN, because capital A is meant to invoke the memory of the vector potential. Now, the reason why this is actually important is if you once you study gauge transformations in quantum mechanics, which you will in quantum field theory perhaps, or maybe even in this class later on, you will see that this quantity, especially when you have an electromagnetic field, then a phase of this kind is very, very common. But now let's not get distracted by that. Let's just look at this one quantity and try to ask a question that was already raised by Rahul, which is, what sense does it make anyway? I can change phi n by changing its phase, right? I can always redefine. Suppose I start with phi n, one bunch of phi n RT, that every R, I have a phi n R. Okay. At every given value of R vector, I have a Hamiltonian. Then I've chosen certain eigenkets for that, and let's say I'm calling those eigenkets the phi n's. So I've made a phase choice. But then I can always change the phase choice, right? I can always do something like this. And not only that, I can make the phase choice different at different times. So as time changes by, I make different phase choices. So wouldn't that change the gamma n? So first question is, if I did this, if I change the phi n's by putting in additional phases, how would the AM change? So let's just get rid of this piece now for the time being. So what we are trying to ask is this. If I were to replace phi n RT by a new phi n RT, simply by saying that instead of using the original phi n RTs, I will use some some new ket like this, just multiplied by a phase factor, which can of course change from time to time. Then can I actually get rid of this gamma n, etc.? Can I change the gamma n to 0, for example? If I can, then it doesn't really make sense to talk so much about gamma n, right? But now let's see how an changes when you do that. What will happen when you plug in an, this new phi n? It will be the new phi n grad r of new phi n, right? So new phi n is of course phi n e to the power minus I mu n. Okay, mu n, the important point is I can change the mu n at different points, different parameter values. So I can change it differently at different parameter values. It could be a function of r. If it's not a function of r, if it's an overall constant, then all that happens when I plug this in is this. If mu n is independent of r, it will just travel through the grad r, hit this and cancel out. So it will not change an, it will not change my gamma n. But actually it does change stuff because mu n can also depend on grad r, on r. So then what you get are two pieces. So I n e to the I minus I mu n times I grad r mu n e to the I mu n phi n right? Now you can see if you were to just cancel out everything, and everything easily cancels out, what happens? E to the minus I mu n here cancels out the e to the I mu n here. I grad r mu n, this is a quantity which does not, this is not an operator any longer, right? Remember, grad r had a non-trivial action on phi n. Phi n depends on r, so grad r phi n change the state. But here, grad r mu n is just a multiplying factor, so it's just going to move out. Oh, sorry, I made a mistake. I made a mistake in the sense that actually I forgot that in the definition of gamma n, or when I defined an, I did just drop the I. Gamma n is the integral of a n r dr. There's no minus I here. The minus I is actually introduced here. That's just a cosmetic thing, but it actually makes the thing look a lot neater. So there's a minus I outside. So this minus I times phi n grad r phi n, that's nothing but the original an vector, whatever the an vector was before. But now you have added an additional piece to it. So does this look familiar? This change? That when you change phi by adding, when you change, redefine phi, by just redefining by multiplying it by different phase factors at different positions, the parameter space, which is perfectly legitimate. You can always do that. And what happens to an? An becomes an prime, which is an plus grad r mu n. Looks familiar? Again, remember we said A sort of is like the vector potential. Then does this look familiar? Yeah, this is exactly the gauge transformation. Okay, that's all it is, a gauge transformation. Okay. And if you do a gauge transformation, does the integral of an prime dn dot dr, which is the gamma n prime, the new gamma n, over this contour, is the same as the old gamma n? Is this true? You can see what exactly it is. It's this, right? That means the new gamma n, once you have redefined all the phases, the new gamma n is actually different from the old gamma n. It's actually mu n RT at the end point. Well, grad r mu n dot dr is essentially nothing but, okay, this is d capital R actually. Grad r mu n dot d capital R is nothing but the dr mu n. So if the orbit, so the point is gamma n actually changes. It becomes gamma n prime if you do a phase transformation, which is exactly what Raoul's point really was. You can change the Barry phase by changing your definition of what your energy eigenkets are by absorbing phases. However, and this is very important, if your path in the parameter space is a loop, then how much is this? Then you start, this is your RT0, some bunch of parameters at time t0. But when the contour is closed, that means you're essentially changing the parameters with time, but after a while you come back to the original values of parameters. Then these two things are exactly equal, right? For a closed loop, gamma n and gamma n prime must be equal. And so you simply cannot choose your phases in such a way that you can make them vanish. The whole point is you can, of course, say, I will just find out what the gamma n is at every stage, and then I will choose my mu n RT in such a way that exactly cancels out gamma n minus mu n RT0. So you get zero Barry phase all the way. You can keep on doing that. But if your parameter loop closes up and you're back where you were, now you no longer have a free choice, right? You have already chosen the phase when you started. You can't now all of a sudden say, no, the phase is going to be something else now. So as long as the contour is closed, you end up with a quantity which cannot be gotten rid of by redefining the phases, which is a hallmark of a physical quantity. A physical quantity simply is something you cannot get rid of by redefining phases. Anything you can change by redefining phases is not really a physical quantity. It doesn't have any physical consequence. But this phase that a system acquires over a closed loop has immense physical significance. It's a geometric quantity, not a dynamical one, but because it does not depend on the rate at which the parameters change, only over the path which you take over the parameter space, not how fast or how slow you take it. And more importantly, if you do it over a closed loop, then whatever phase you acquire is something which is independent of whatever phase choices you make. Okay. The analogies between these and things you will learn, say, next semester about, say, if those of you who take general relativity would know that if you started at a point in a curved space time and went all the way down in a loop, keeping the vector parallel to itself throughout, at the end it will turn around. It will not be in the same direction. All of you know this, right? This is something which you know from elementary popular science lectures. This thing is also very similar. In fact, mathematically, it's the same effect in a different situation. There's a whole class of physical phenomena which occurs basically because of this. In fact, the whole branch of topological insulators, for example, a major part of that depends on, not all of it, but a major part of this does depend on the fact that you can occur a non-trivial phase around a closed contour like this. So I'm just telling you this as a sort of introduction to this, because next semester when you talk about advanced condensed matter or general relativity or whatever other advanced courses, you will actually see effects of this thing occur in many different places. They look slightly different at every place because we're talking of different contexts and so on. But the basic mathematics is really all the same. So this part is what I wanted to introduce to you, because this is an interesting feature about modern quantum mechanics, which has quite a lot of implications. It's not just a curiosity. And you will see, okay, I will not give you the applications for this in this course simply because I would have to go too far into other topics to do that. But I can guarantee you that when you later on study things like say topological insulators in condensed matter or anholonomic effects, which is a big thing, but basically effects of curvature in general relativity, you will essentially see the same thing occur over and over again. But I also wanted to make you familiar with the way you handle Schrodinger equation for time-dependent cases, because that is the next major topic. By the way, today's lecture does not complete the WKB thing. I wanted to complete it in one lecture, but found that it's going to get too long. So there will be one, hopefully shorter lecture, which will just discuss two topics. One is tunneling, the other is something like a double well potential, special features that occur there. But after that, we are going to go into time-dependent perturbation theory, and the final topic we will study in this course is scattering after that. Okay, now I will stop this class, but I have one request, especially to one person, Anubhav Nandi. I want you to stick around after the others leave. Okay, I have something to discuss with you.
Okay, sir. Okay.
And for the rest of you, okay, let me make the announcement even right now, which is Friday. Okay, you all know what comes when I say Friday, right? Yeah. What comes when I say Friday? Yes? Okay, but not Friday, not 9th, but Friday 16th. Usual time, I keep on confusing that, but I think it's 2:30 p.m., right? And the class test will be essentially on the WKB method. That means, I don't remember the lecture numbers, you just figure out. Up to this one and the next one.
We have a test this Friday also, right?
This Friday, you have a test.
You said something about 9th.
No, I said not 9th. I said not on the 9th, but on the 16th. I mentioned the 9th simply because Friday means 9th also. Not on 9th, on 16th. Okay. So now let's call it a day, but Anubhav, stick around. I want to discuss something with you.
Okay.
Everybody else, go away.